Saturn's rings are dying, not from some sudden catastrophe, but slowly, continuously right now as you're listening to this. And there's a tiny moon, barely the size of a small city, that's been caught in the act of physically carving apart one of the most delicate structures in the entire solar system. It's called Daphnis. It's 8 kilometers across, small enough that you could walk its full length in under 2 hours if you somehow found solid ground to stand on. And decades of imagery from NASA's Cassini spacecraft, now given fresh, high-resolution infrared detail by the James Webb Space Telescope, show it doing something genuinely remarkable, kicking up walls of ice 1.5 kilometers high every single time it passes through a narrow gap in Saturn's rings. Everybody, this is the real, documented, scientifically verified story of what's actually happening to Saturn's rings, and it doesn't need a single exaggeration to be genuinely alarming. Real research, published in real peer-reviewed journals, shows these rings are eroding, they're disappearing, and current estimates suggest they might already be younger than the dinosaurs. Let's start with Daphnis itself, because it's one of the strangest, most visually dramatic small moons in the entire solar system, and almost nobody outside dedicated space enthusiasts has ever heard of it. Daphnis orbits Saturn inside a narrow 42-kilometer wide break in the planet's massive A ring called the Keeler gap, a gap that exists specifically because Daphnis' own gravity has swept it clear of ring material over time. Astronomers first suspected something was living inside that gap years before they actually confirmed it, because they kept noticing strange, rippling disturbances along the gap's edges, gravitational fingerprints that could only be explained by a hidden, embedded moon exerting its pull on the surrounding ring particles. NASA's Cassini spacecraft finally confirmed Daphnis' existence directly on May 1st, 2005, capturing images that showed the tiny moon exactly where those ripples had predicted it would be. It's worth understanding a bit about Saturn's ring system as a whole before diving deeper into what Daphnis specifically does to it, because the scale involved is genuinely difficult to picture accurately. Saturn's rings aren't a single solid structure at all, despite how they appear from a distance. They're made up of billions of individual chunks of water, ice, and rock, ranging in size from particles smaller than a single grain of sand, all the way up to boulders the size of a house, all orbiting Saturn together in a broad, flattened disk. That disk is almost unbelievably thin relative to its width, spanning roughly 280,000 kilometers across, wide enough to lay more than 20 Earths side by side, while measuring, in most places, somewhere between just 10 and 100 meters thick, a ratio so extreme that if Saturn's rings were scaled down to the width of a football field, their actual thickness would be thinner than a sheet of paper. That extraordinary thinness is precisely why a moon as small as Daphnis, at only 8 kilometers across, can still exert a genuinely dramatic, visually obvious effect on the ring material immediately surrounding it. Since even a comparatively small gravitational tug is enough to meaningfully disturb a structure this delicately thin and precisely balanced. The ring system itself is organized into several major, named divisions, labeled alphabetically in the order they were discovered rather than their actual position from Saturn, with the main rings visible through amateur telescopes, labeled the C, B, and A rings moving outward from the planet, separated by gaps of varying width where gravitational interactions with nearby moons have swept the material clear. The Keeler gap, where Daphnis makes its home, sits near the very outer edge of the A-ring, roughly 250 kilometers from where the outermost major ring division actually ends. It's a genuinely narrow gap on the scale of the ring system as a whole, only slightly wider than Daphnis itself, which is exactly why the little moon's gravity is powerful enough to noticeably perturb ring particles across the gap's entire width, rather than simply carving out a clean, empty lane and leaving the surrounding material otherwise undisturbed. What makes Daphnis genuinely remarkable isn't just that it exists, tucked into this narrow gap. It's what its gravity actually does to the ring material surrounding it, in real time, with every single orbit. Daphnis' orbit isn't a perfect circle. It's very slightly elliptical, drifting closer to one edge of the Keeler gap and then the other by a margin of only about 9 kilometers, a genuinely tiny variation on a cosmic scale, but enough to matter enormously given how delicately balanced the ring material actually is. On top of that slight orbital eccentricity, Daphnis' orbit is also tilted just barely by a mere 0. 0's 3/6 degrees relative to the flat plane of Saturn's rings. That's an almost imperceptibly small tilt. But because Daphnis orbits Saturn so many times, that tiny tilt causes the little moon to bob up and down out of the ring plane by as much as 17 kilometers with every single pass. Combine those two factors, the slight elliptical wobble and the slight vertical bobbing, and you get exactly what Cassini's cameras captured in stunning, repeated detail across the mission's 13 years orbiting Saturn. As Daphnis moves through the Keeler gap, Its gravity reaches out and tugs on the icy particles lining the gap's edges, pulling them up out of the flat ring plane entirely, forming towering wave-like crests that can reach roughly 1.5 kilometers in height. Structures cast into sharp relief by dramatic shadows during specific lighting conditions around Saturn's equinox, when the sun's angle to the ring plane drops low enough to make these vertical structures stand out in genuinely spectacular fashion. Cassini imaging scientist Kevin Gill, whose visualizations helped popularize just how dramatic this effect actually looks up close, described the underlying process in straightforward terms, explaining that material on the inner edge of the gap orbits faster than Daphnis itself, so the waves generated there lead the moon in its orbit, while material on the slower-moving outer edge trails behind it instead, producing a rippling, scalloped pattern along both edges of the gap simultaneously, one leading, one trailing, generated by the exact same small moon passing through the middle. If a real, visually stunning, scientifically documented phenomenon like this, gravity physically sculpting ice into waves in real time, is exactly the kind of space science you come here for, subscribe now, because Daphnis's wave-making is genuinely just the opening act of a much bigger, much more consequential story about what's actually happening to Saturn's entire ring system. Because here's where this story moves from a fascinating localized gravitational curiosity to something with genuine consequences for the rings as a whole. Linda Spilker, project scientist for the Cassini mission at NASA's Jet Propulsion Laboratory, described Daphnis's broader role directly and plainly during the mission's final close flyby of the little moon in January 2017. She said the gravity from this incredibly tiny moon is creating the Keeler gap and actively sculpting Saturn's magnificent rings, a direct, on-the-record acknowledgement from the mission's own lead scientist that this 8-kilometer speck of ice is genuinely, physically reshaping one of the largest, most visually iconic structures in the entire solar system. During that same final flyby, Cassini's cameras caught something even more dramatic than the usual wave pattern. A thin, narrow tendril of ring material that appeared to have been directly ripped straight out of the A-ring by Daphnis's passing gravity, trailing behind the moon in its orbit like a wisp of smoke pulled from a much larger cloud. Daphnis isn't unique in this specific role either, though it is one of the most visually dramatic examples astronomers have documented. Saturn's ring system includes several small moons that function this way, gravitationally shepherding the edges of specific gaps and structures within the rings. A larger moon called Pan, sitting inside a separate wider break in the A-ring known as the Encke gap, performs a broadly similar function, though Pan carries nearly 100 times the mass of tiny Daphnis, and correspondingly carves a considerably wider gap as a result. Other small moons, including Atlas, Prometheus, and Pandora, perform their own versions of this gravitational shepherding role elsewhere throughout Saturn's ring system, each one keeping specific ring structures confined, sculpted, and, in some cases, actively torn at along their edges. What all of this reveals, and what genuinely surprised planetary scientists once Cassini's detailed long-term imaging made it fully clear, is that Saturn's rings were never the static, unchanging, purely decorative structure they'd long been imagined to be. They're a dynamic, constantly evolving system, actively being pushed, pulled, and reshaped by the gravity of the small moons embedded directly within them. Daphnis's own physical appearance adds yet another layer of genuine strangeness to this story, one that Cassini's closest ever flyby, conducted in January 2017 at a distance of roughly 28,000 kilometers, captured in remarkable detail. Rather than being a simple, roughly spherical chunk of rock and ice the way many small moons appear, Daphnis has a genuinely odd, almost flying saucer-like shape, measuring approximately 8 kilometers across, but only about 6 kilometers in height, with a distinct ridge running around its equator, and a second, fainter ridge visible at higher latitude. Researchers studying that imagery believe the moon's unusually soft, smoothed-over appearance, with craters and surface features that look notably less sharp and well-defined than on many other small moons, is likely caused by a continuous, gentle coating of fine ice grains drifting in from the surrounding rings themselves, gradually settling onto Daphnis's surface over time and softening its features the way a light, continuous snowfall might smooth out a rocky landscape here on Earth. In a strange, quietly poetic sense, the same ring particles Daphnis spends every orbit disturbing and reshaping are also, slowly, continuously, reshaping the little moon right back, coating it in a fine dusting of the very material its gravity keeps disrupting. That dynamic, actively evolving picture connects directly to the second, considerably larger piece of this story, the discovery that Saturn's rings aren't just being locally reshaped by moons like Daphnis, they're genuinely disappearing, and scientists now have a real measured rate for exactly how fast that's happening. Data gathered during Cassini's grand finale, the dramatic conclusion to its 13-year mission in which the spacecraft deliberately dove through the narrow gap between Saturn and its innermost rings, before ultimately plunging into the planet's atmosphere in September 2017, revealed something researchers had suspected for years, but had never been able to measure with this level of precision, a phenomenon scientists call ring rain. As Saturn's rings orbit the planet, ultraviolet light from the sun and impacts from tiny meteoroids constantly knock loose electrically charged ice particles from the ring material. Those charged particles then get captured by Saturn's powerful magnetic field, which funnels them directly downward, away from the rings entirely and into Saturn's upper atmosphere, where they essentially rain down and are permanently lost from the ring system. The underlying physics of that process connects directly to how Saturn's magnetic field itself is structured. Unlike Earth's magnetic field, which is tilted at a meaningful angle relative to our planet's rotational axis, Saturn's magnetic field is almost perfectly aligned with its spin, meaning the invisible magnetic field lines threading through the space around the planet trace out a remarkably symmetric, predictable pattern. Because Saturn's rings sit directly within reach of that magnetic field, charged ice particles knocked loose from ring material effectively get captured and guided along those field lines, like tiny beads sliding down a wire, funneled directly towards specific latitude bands in Saturn's upper atmosphere, where those field lines eventually intersect the planet itself. Researchers have actually detected the visible signature of this process directly, observing distinct dark bands in Saturn's upper atmosphere at precisely the latitudes where models predicted this ring material should be raining in, essentially watching, in real time, exactly where billions of years' worth of ring material has been quietly draining away into the planet below. Cassini's own instruments, measuring this process directly during those final, close orbits, calculated that Saturn's rings are shedding approximately 10,000 kilograms of material this way every single second, an amount some researchers have vividly compared to an Olympic-sized swimming pool's worth of ice raining into Saturn roughly every half hour. James O'Donoghue, a planetary scientist who has studied this phenomenon extensively using both Cassini's own data and follow-up ground-based observations, has described the ring rain process as happening fast enough that it's actually degrading the ring system at the maximum rate estimated from Cassini's own measurements, underscoring that this isn't a slow, negligible background process, but a genuinely significant ongoing drain on the total amount of material the rings actually contain. At that measured rate, researchers have calculated that Saturn's entire ring system could be completely gone within somewhere between 100 and 300 million years, a number that sounds almost incomprehensibly distant on a human timescale, but represents a genuinely short window in the context of the solar system's overall 5 billion year history. One NASA scientist summarized the broader implication of these findings plainly, stating directly that massive rings like Saturn's simply do not last long, a genuinely striking admission when you consider that Saturn's rings have long been treated as one of the most iconic, seemingly permanent features in the entire solar system. That timeline connects to an even more surprising piece of research that emerged from continued analysis of Cassini's data, findings that fundamentally reshaped how scientists think about the rings' history, not just their future. For decades, many astronomers assumed Saturn's rings were essentially as old as the planet itself, a leftover structure from the solar system's earliest formation, 5 billion years ago. Cassini's precise measurements of the ring's total mass, combined with detailed models of how quickly that ring rain erosion process would have been depleting that mass over time, led researchers to a genuinely different conclusion. Multiple independent studies analyzing this data have concluded that Saturn's rings are likely far younger than the planet itself, quite possibly less than 100 million years old, meaning these iconic rings may have formed sometime during the same broad era in Earth's own history when dinosaurs were still walking the planet's surface. If that estimate holds up, it means humanity happens to exist during a genuinely narrow, almost coincidental window in cosmic history, a window when Saturn happens to have its famous rings at all, rather than that ring system being some kind of permanent, defining feature that's simply always been there since the solar system's birth. If genuinely humbling science like this, the kind that reframes something you've looked at your entire life as something temporary rather than permanent, is exactly what you come here for, subscribe now, because there's still an active, ongoing research effort trying to pin down exactly how fast this erosion is actually happening right now, using instruments considerably more sensitive than anything available even a few years ago. Because this is precisely where the James Webb Space Telescope enters the story, and its role here matters enormously for understanding where this research actually stands today, in 2026. Well, on June 25th, 2023, Webb captured its first ever near-infrared observations of Saturn using its NIRCam instrument, and the resulting images revealed something genuinely striking. At the specific infrared wavelength Webb was observing, methane gas in Saturn's atmosphere absorbs almost all of the sunlight reaching the planet, causing Saturn itself to appear remarkably dark in the image. The icy rings, by contrast, remained relatively bright, since ice reflects that particular wavelength of light considerably more efficiently than the gas absorbing it does. producing an unusual, almost inverted appearance where the rings visually dominate over the planet they surround. That contrast isn't just a striking visual effect. It's scientifically valuable because it lets researchers study the ring's composition and structure in a level of detail that's difficult to achieve using visible light alone, where the glare from Saturn itself tends to compete more directly with the fainter ring material for a telescope's attention. Since that first 2023 observation, Webb has continued regularly imaging Saturn as part of an ongoing, coordinated research effort alongside the Hubble Space Telescope, with new images released as recently as March 2026, capturing the planet's rings and atmosphere in remarkable, continuously updated detail. Researchers studying Saturn have specifically highlighted Webb's potential to meaningfully refine the ring rain measurements Cassini first gathered, given the telescope's exceptional sensitivity to exactly the kind of faint infrared signatures associated with this ongoing erosion process. As one researcher involved in this continuing work put it directly, the plan going forward involves taking measurements over the coming decade specifically to track how the rate of ring rain actually changes over time, then extrapolating those results across a full Saturnian year, which lasts approximately 29 Earth years, to build a genuinely complete picture of how this erosion process behaves across every season Saturn experiences during its long orbit around the Sun. Researchers specifically want to use Webb's, in their own words, ridiculously high sensitivity to nail down a more precise estimate of exactly how much material the rings are actually losing, refining the current 100 to 300 million year lifespan estimate into something considerably more exact than what Cassini's more limited final orbit measurements alone could provide. There's an entirely separate mystery Webb and Hubble have been working together to solve as well, one that connects to the same broader story of the rings as an active, evolving system rather than a static one. Saturn's rings periodically display strange, transient dark markings called spokes, features first properly documented by NASA's Voyager spacecraft back in 1981 and studied in extensive detail throughout Cassini's own 13-year mission. These spokes appear to be caused by extremely fine dust particles, electrically charged and levitated slightly above the ring plane by processes connected to Saturn's powerful magnetic field, though the precise mechanism responsible for that charging and levitation still isn't fully understood, even now, 45 years after Voyager first spotted the phenomenon. The spokes follow a seasonal pattern, becoming more prominent as Saturn approaches its equinox roughly every 7 years, and Hubble has continued monitoring each returning spoke season, with the most recent extensively documented instance occurring around Saturn's May 2025 equinox. That equinox event carries its own separate significance worth understanding clearly, because it's routinely and incorrectly confused with the ring erosion story in casual reporting. When Saturn reached its equinox in 2025, Earth passed directly through the plane of Saturn's rings, and because the rings themselves are almost unbelievably thin, in some places as little as 10 meters thick despite spanning roughly 280,000 kilometers in width, wide enough to lay more than 20 Earths side by side, they became nearly invisible from Earth for several months, appearing edge-on as a thin, barely visible line, rather than their usual, dramatically tilted, fully open view. That specific vanishing act was purely a matter of geometry and orbital alignment, a predictable, harmless event that happens roughly every 15 years as Saturn's own 26. 7-degree axial tilt carries the ring plane directly into our line of sight. It has absolutely nothing to do with the genuine, ongoing physical erosion process actually reducing the ring's total mass over millions of years. Conflating the two, a temporary viewing illusion and a genuine, permanent, ongoing mass loss, remains one of the most common mistakes in casual coverage of this entire topic. And it's worth being precise about the difference here specifically, because getting it wrong badly understates just how remarkable the real, ongoing erosion story actually is. There's a broader scientific significance to all of this research that extends well past simply tracking how quickly Saturn's rings happen to be disappearing. A study published in the journal Nature Communications in 2026 laid out this bigger picture directly, describing how Cassini's mission fundamentally revealed that Saturn's rings actively supply material directly into the planet's own atmosphere, functioning less like a separate, independent, purely decorative structure orbiting above the planet, and more like a genuine active participant directly coupled to Saturn's own atmospheric chemistry and its ionosphere, the electrically charged upper layer of the planet's atmosphere. The study's authors noted that Webb has since sharpened that same picture considerably, even while acknowledging that meaningful pieces of the full story, including exactly how the composition and rate of this erosion process varies over time, and precisely how long the rings genuinely have left, remain areas of active, ongoing, unresolved research, rather than settled scientific fact. So here's where this leaves us, and it's a genuinely remarkable picture once you put every piece together properly. A moon barely the size of a small city, discovered because of the gravitational ripples it left behind before anyone had actually seen it directly, spends every single orbit physically sculpting 1.5 kilometer tall waves into the icy edges of a gap in Saturn's rings, a real, documented, photographed phenomenon confirmed repeatedly across Cassini's 13 years at Saturn. Meanwhile, the rings surrounding that same small moon are measurably, continuously eroding, raining in Olympic swimming pools worth of ice into Saturn's atmosphere roughly every 30 minutes. A genuine, physically confirmed process that could see the entire ring system vanish completely within the next 100 to 300 million years, a system that may itself be far younger than the planet it surrounds, quite possibly younger than the dinosaurs that once walked Earth. James Webb, working in coordination with Hubble, is actively refining exactly how fast that erosion is happening right now, building toward a considerably more precise understanding of Saturn's rings than Cassini's own final measurements alone could ever provide. None of that requires a single exaggeration to be genuinely worth your attention. Saturn's rings, one of the most recognizable, most photographed structures anywhere in the solar system, really are actively being carved apart by the gravity of tiny, embedded moons, and really are slowly, measurably raining away into the planet they surround. A real, ongoing, scientifically documented process happening right now, whether or not anyone happens to be watching. If genuinely remarkable, fully verified space science like this, the kind that reveals a familiar iconic structure to be far more temporary and dynamic than most people ever realized, is exactly what you come here for. Subscribe and turn on notifications, because Webb's ongoing observations of Saturn's rings are continuing right now, and we'll bring you the next update the moment new findings are published.